In the previous lecture, we had first looked at conservation of momentum and how it's really just a restatement of Newton's third law of motion. And it's very important when we do conservation of energy that we don't take into account external forces, assuming that they're small enough for us to not take into account. We also use conservation of momentum usually when there are collisions and things happen too fast for us to see the specifics of what's taking place. Now I'm going to go back to this interactive physics example, and one thing that I did was I turned off friction. I just thought it would be easier if we don't have friction involved. And we can take these and they bounce into each other and bounce off, and it works out pretty nicely. Now one thing that I did here was I changed the elasticity, and what I'm going to do is I'm going to take these guys and I'm going to duplicate them and move them off of the surface. I'm going to have them so that they're lined up maybe a little bit more nicely with each other here, and I'll just go ahead and turn off gravity here. So let's say no gravity. And now what happens is they hit each other, and you can see that different things occur. These ones obviously go crazy. We'll just ignore those for now. But these two stick together with each other perfectly. So we had 4 and 6 as the velocities, and I'm just going to go ahead and measure the velocities of these ones as well. And we know that they start off with 4 and -6, and afterwards it's looking like they have the exact same velocity, and it's half of the initial velocity of the first block. I'll go ahead and put on velocity for this one as well. Not sure why that's coming up for us, but here we go. Okay, so there we are, and you can see that occurring. Now that was with an elasticity of 0. I could also do something like an elasticity of 1. And if we run this one, we get very different effects happening than what we had before. This one just suddenly stops, and this one goes flying off in the other direction at a very high speed. So these two collisions that we've seen, the first one, where they stuck together, was what we call a perfectly inelastic collision. This second one that we saw, where the elasticity was 1, is a perfectly elastic collision. It's really just called an elastic collision. And anything in between, let's say I make this 0.8 and this one 0.8 as well, anything in between is known as inelastic. So it's not perfectly inelastic, but it is somewhere in between. Okay, and the closer I make these to 0, the closer it'll look like to a perfectly inelastic collision. Now to give you a rundown on how the different collisions work, I've made this spectrum of elasticity, and on the one hand we have elastic. In the middle, everywhere in the middle between these two endpoints, we have inelastic, and at the very end we have something called perfectly inelastic. This is where they stick together. And so one of the things I'm going to do is just kind of describe fairly briefly some major points with these things. So I've added a couple of descriptors here. Under elastic, they sure can bounce. That's the idea behind an elastic collision. They bounce like crazy. With perfectly inelastic, they done got stuck together. That's the best explanation for it. You never have a perfectly inelastic collision where they don't get stuck together. That's the definition of it. That's the nature of it. Now, as far as what really happens, in all cases, momentum is conserved. So I'm not even going to bother to write that down. Momentum is conserved in all cases, assuming that we can ignore the external forces like friction and that type of thing, if we have our system of objects that are colliding with each other isolated. Elastic makes it so that the initial kinetic energy is also equal to the final kinetic energy. So there was no loss of energy from that system due to heat. There's no conversion of energy from kinetic energy to gravitational potential energy or anything like that. This is the case. Now for perfectly inelastic, this is less concise. You still have to conserve momentum, right? And I guess I will write it down over here. So you're still conserving momentum. There's no question about it. But you lose the max kinetic energy as possible while still maintaining conservation of momentum. Now, how does this work? To give you an idea, let's say that you have two trains coming towards each other. They're equal masses, equal speeds, they're just going in opposite directions. So the momentum of that system will initially be zero. They could have a lot of kinetic energy, but if the initial momentum of the system is zero, that means that the final momentum of the system also has to be zero. Well, what that means is that if you have momentum initial equals zero, which equals the final momentum of the system, and they stick together, so you've got one train and you've got another train and they've stuck together, they can't be going this way because that would give them a positive momentum. They can't be going this way because that would give them a negative momentum. They have to be having a zero momentum at the end. And they're stuck together, so they both have to be doing the exact same thing. Initially, you could have one train going this way and you could have the other train going the other direction. That's great. You can have a momentum of zero. Okay? But once they stuck together, the only way to have a momentum of zero is if they're not moving. So in that case, we lost all of the kinetic energy of the system. But in the case with the two blocks in interactive physics, one block was much larger than the other block. The result was that this one ended up, because their speeds were fairly similar, this one ended up dominating. So if I looked at the total momentum of the system, this one had a larger amount of momentum than this one. That meant that even when they got stuck together, they had an overall motion towards the right. So we lost as much kinetic energy as we possibly could, but we had to maintain some because momentum was still conserved. It's a little bit tricky, but that's probably the best way to go about thinking about it. Now what I'm going to do next is just do a quick example problem of a perfectly inelastic collision. So in this example, I've decided to change things up a little bit, and I'm going to have both of these objects initially going in the same direction. So M1 will be 4 kilograms at 60 meters per second, M2 2 kilograms at 2 meters per second in the same direction. We can have collisions where both objects are moving in the same direction. What this does is it assures us also that I didn't make it so that the final conditions will be zero momentum. And then after the collision, and I typically draw a before and an after, in this case they're stuck together because I know that this is a perfectly inelastic collision because that's how I set it up to be. And they each have the same velocity, so I'm not going to bother with v1 and v2. They're just going to have the same velocity. So what this will look like then is we'll have momentum initial equals momentum final. And initially we have m1 v1 plus m2 v2, and that's going to equal the final state, which will be m1 plus m2. They're stuck together, so I can treat them as one mass, times v prime, their overall final velocity, since they're stuck together. And so this is a pretty easy problem to solve. All I have to do is kind of rearrange this equation a little bit, and we should be able to do this. Divide by m1 plus m2. So I have m1 v1 plus m2 v2 divided by m1 plus m2, and that will equal v prime. So I'll plug in some numbers and I'll have 6 times 4 is 24 plus 4 divided by the total mass, which is 6, and so we have 28 sixths, or what would that be? Something like 4 2/3 meters per second will be the final velocity. So it's going to be going somewhere in between the speeds of these ones. And we have actually, if we look at the kinetic energy that's involved in this, if we actually do go through the process of adding all that up, what we'll find is that we've lost a substantial amount of kinetic energy. And here I've just quickly outlined the amounts of energy that were actually present. T2 being small and not very fast only had 4 joules of energy. The first block being larger and also much faster had quite a lot of energy, giving them a total initially of 76 joules. And we see that after the collision, they only had 65 joules. So this was not a huge loss of energy, in part because they were both going in the same direction. It's kind of like if two cars bump each other and they're both going in the same direction, the collision isn't that massive. There's not a whole lot of energy lost necessarily, as long as they're going, reasonable speeds compared to each other. And that's what happened in this case. If I had turned around this block right here so that it was headed this way, we would have seen a substantial loss in terms of its energy. Primarily because if we look down here, this would have been 24 minus 4 divided by 6. So we would have had, instead of 4 2/3, we would have had 3 1/3 meters per second. And then when we go and calculate that energy, obviously that's going to be a lot less because these two didn't change, and this will be substantially less in terms of the amount of energy that's conserved. So just to briefly reiterate what we did in this lecture, we looked at the different sort of spans of elasticity, from perfectly inelastic, where we lose as much kinetic energy as possible, to the broad range of inelastic, which is where most collisions fall, where you get collisions where some energy is lost, but not necessarily that much, and the elastic, which pretty much never occurs, where no energy is transferred out of kinetic energy of the system.